higher dots per inch means a higher resolution of an image. So you have some box like this, and how many values you want to take like this represents your sampling. So your sampling rate is just how many values you're taking, and quantization is basically what range of values you want to take. So between 0 and 1 you can have infinitely many values, right? But when we're dealing with this digitally, we don't really want to have those infinitely many possibilities. So you can take like maybe 0 to you can take it in steps of 1 by 255. So that'll be an 8-bit input. Or some between 0 and 1 you can have 512 inputs. So basically that's our quantization. So we quantize that 0 to 1 into so many bins, and each bin will contain a certain small value. So yeah, so everyone's cool, right? If you have any doubt, stop me. Okay, I'll do it again. So you guys understood what sampling and quantization are, right? This is like an overview. Like it's a deep topic which I'm not going into too much here, but this is basically what the gist of it is. So the 0 and 1 looks kind of raw, right? Like 0 and 1, you can't really appreciate visually what a 0 or a 1 is. So what we do is we assign 0 to a completely black color and 1 to a completely white color. So when we do that, we'll be able to what this matrix is. So 0 and 1 represent is just the intensity of that pixel. Pixel is picture element. Okay. So here is a little bit of code. Okay, I'll share this IPython notebook with you guys later, so you can run the code yourselves and figure out what is actually happening. Matrix has been converted into this chessboard kind of a thing. So this chessboard basically 0 represents the black pixels and 1 represents the white pixels. So this is what we see, and this is what the computer sees. Okay, so this is what we feed into the computer, and this is what we get as our output. But yeah, so this is basically a binary image. In binary, basically we deal only with 0 and 1. There's nothing else. No other information can be represented. But 0 and 1 is often convenient, and it's like short for storage, and it's also easy for transmission, and hence it's actually convenient in a lot of cases. So okay, there's like a little bit of, I've added a little task here. So maybe like once I give this to you guys, you can probably like try to generate a randomized thing. Instead of, right, you can just create randomized pixels, and okay, you can just try it out later. You can probably come back to it in the end also if you have some time. So okay, next thing is we'll have to see how to represent an image using an intensity plot. So instead of using 0 and 1, we say 0 to 255 for an 8-bit image, and for an 8-bit image, again, yeah, then 255 is bright or dark a pixel is, that shows us what color it is. Okay, that's in grayscale actually. 0 is completely dark, 255 is completely bright, and I'll just pull up an image. So this is the intensity plot of a certain image that I took. Okay, so you can see like there are a lot of peaks here, right? So red is basically where the image is very bright, and blue is basically where the image is very dark. Okay, so actually if I just zoom in, I guess. Yeah, you guys can just see it now, okay? So, basically completely, like blue is basically completely dark or 0. Red is completely white or 1, and if you look at it from the top, you can actually see a kind of a person's face, right? Can you make out that face? Is this image, okay? Which I basically, whenever it is bright, you set the high, and whenever the image is dark, you set it as low. And you get this. Okay, the image is actually, because I plotted it wrong, but that's okay. So this is what it looks like from the top, but actually it's just an intensity plot. So this is how we actually represent images in any digital system. So whenever I talk about image from now, I'll be talking only about digital images. Okay, just keep that in mind. So that's what an image is. So next, to figure out how to read an image. So again, there's a little bit of code here. So cv2.imd, I'll be using OpenCV. If any of you like have worked with it before, this should be pretty straightforward for you guys. Otherwise, you can just go through this and you'll be getting a gist of what reading an image in OpenCV is and subsequent OpenCV functions, which will become much simpler. Okay, so we just say img is equal to cb2.imRead images plt.imShow. It will show us our image. And let's look at the dimension of our image. It says 220, 220, which means there are 220 pixels this way, 220 pixels this way. And if you look at it, you can actually see the values of that image. So it basically goes from 161, 160, 160, just shows the value of how bright or dark it is. And if you look at this plot here, you can see like it goes from like basically like 160, and this is probably like 47, it's basically very low. So this is how we represent our, so this is how this image is digitally represented. Okay, so do any of you have any doubts or anything? It's cool, right? So basically when we deal with images, this is basically y and this is basically our x. Okay, so yeah, that's pretty straightforward. So send the image as an intensity plot of x. So we can actually look at an image as a mathematical function I of x comma y, where x and y will be two independent variables, and I will tell us how bright or dark that particular pixel is. Okay, so first what we dealt with was black and white, and the next is a grayscale image. Okay, so grayscale is 0 to 255, and now we'll try to look at images. Oops, something is wrong, right? So this image, when we read it, it's coming somewhat blue. Okay, so this is because of a peculiarity in the way OpenCV and Matplotlib read images. So to first look at actually what that image, color image is represented as, let's just print out the dimension. See, it's 220, 223, right? So do any of you know, like, so 220, 220, you all know what it represented, right? So what do you think this? So now 220, 223 basically means there are 3 channels. So do you all know what those 3 channels could be? RGB, right? Okay. So red, green and blue, except that, yeah, so let's just print it out. So, and you can see that there are again 3 matrices each dealing with red, green and blue. It caused the weirdness in that image we loaded and why did it look blue. So the problem is that OpenCV deals with images as B, G and R, while Matplotlib deals with it as R, G and B. So what happens is basically all these, the red and blue got flipped. So wherever your actual image was supposed to be red, it became blue and became red. This looks highly. So basically they just got flipped. So that's one thing you always have to keep in mind when using OpenCV. So this is like a little small thing that will probably like ruin like your code, and you'll probably spend hours looking at what went wrong, but it's actually just that these 2 things are flipped. So yeah, that's it. And yeah, so here I just did img is equal to little code, just flip these 2 channels, and you print it out, you get this. So that's convenient, except that OpenCV has this function called convert color, which actually makes this thing pretty simple for us. And this is how an image, RGB image, could be looked at. So you have a okay, so this is 255, 255, 255, which represents white. This is 0, which represents black. And you can take your 3 axes as red, blue and green. So where red and green meet, it will be yellow. Where blue and green meet, it will be cyan. And where red and blue meet, it will be magenta. So, you know, like how you have R, G and B, right? So this is basically a color space, which basically says what our bases are. So do you guys know what bases are in linear algebra? Yeah, so basically bases are a set of independent vectors with which you can span your entire vector space. So this little deviation here, you have your y, You have your x, okay? So you know what vectors are, right? Everyone's cool with the concept of vectors, right? So I give you any vector x comma y. Can you represent it as a sum of two independent x and y vectors? Yeah, and how would you do that? Yeah, a linear combination of two vectors. And which two vectors would you choose for convenience? Perpendicular vectors. Which two perpendicular vectors? Sorry? Someone just raise your hand and say what you think the answer is. No, I mean, all of you just said it, right? So just say it, anyone. I cap, j cap, right? So what is I cap and j cap actually? Yeah, so I cap is basically 1 0, j cap is basically 0 1, right? So with 1 0 and 0 1 you can represent any vector. So similarly in our color space we have three bases, okay? This is our R bases, G bases, B bases, 0 0. And a linear combination of these three will be able to produce any color we need. So that's basically what this Cartesian space refers to. So this linear combination of any of these three colors can be used to produce any other color in the range black to white, right? So I understood this, right? Yeah. So if anyone has any doubts, you can stop me here. Okay, you want to note it down or something? So once you note it down, just let me know, I'll move on. Okay, quick question for the other guys who are actually right. So, can you think of any other thing we can use instead of R, G and B to actually represent any color? So, Cmyk, I actually heard an answer, that's actually what I was looking for. So, Cmyk is another very simple color space that we deal with. So, an analogy would be instead of taking x and y, we can take some vector here and some vector here, right? As long as they're linearly independent of each other, we can actually choose any two vectors to span our vector space. So similarly, we use Cmyk, which is basically 1 minus RGB. K just represents black, okay? So 1 minus basically you do white minus RG and B. So if you remove white from RGB, or if you remove white from red, you get green plus blue, which is cyan. You remove green, you get blue plus red, which is magenta. You remove red, you get blue plus green, yellow. And you remove white from white, you get black. So that's just an alternative way of looking at the same vector space. So basically any space you have in signal processing or linear algebra can be looked at from multiple angles. So one would be your RGB angle, another one would be your Cmyk angle. So this is multiple things. So later on you probably this time domain, frequency domain. So you can look at it in the time domain or look at it in the frequency domain based on your convenience. So this is just a simple example. So next, I'll just move on. No? Yeah, color conversion and smoothing. Okay. So I'll just actually erase this now. Out of the some guys walked in late, right? Probably meet up with me later. I'll just get you briefed up. We'll have to look at conversion of color from one space to another. So we already saw our grayscale space, right? So we need to convert it to, sometimes we'll have a need of converting grayscale to black and white. So do any of you know any way of converting grayscale to black and white? So it's very simple, just think intuitively. I don't want an answer, a technical word. So how would you convert some continuous variable to a discrete variable? sorry, yeah, basically you put a limit. So let's say you have something like this. Okay, so this is some continuous variable. Okay, and now representing this is kind of a pain, right? So what we do is simply we just put a line here. Whatever is above the line, you just say that it's a 1. Whatever is below the line, you say it's a 0. So it goes 1, 1, 1, 1, 1. Below the line 0, 1, and so on. So we can actually do the same thing with our grayscale image. So this is what we look at called as thresholding. Okay, so thresholding is basically an algorithm where which we use to convert some grayscale image into a black and white image. So you all know that we have some values, right? So we again just set a limit, say 7. It's basically the midpoint of 0 and 255. And if any pixel is greater than 127, we set it as 1. If it's lesser, we set it as 0. So we just get something. Okay, so basically the opposite of, like, not opposite, it's, yeah, okay, you just get it, right? So what it is, that checkerboard would become like getting something to that checkerboard basically. So again, see some bit of code, you guys can run it later. Actual image, okay? So here this is basically 0 and this is 255. This is basically the smooth gradient. And once we apply a thresholding of 127, what do you think will happen? Yeah, precisely. Back half white. We also have some other functions. Let's probably run it through with you guys so you get what's happening. So if we do binary inverse, basically flips it. Binary inverse is just white and black. And then truncate. Yeah, so basically, can you guys tell me what happened there? So actually we thresholded the image, but we didn't get a binary image. So can you guys tell me like what exactly happened? Yeah, so put a cap here. And we said whatever is above you keep that. Whatever is above you turn it into a 1. Whatever is below you keep that value. Right? So what would have happened is whatever is above become a 1. If it's below you'll get like this. If it's 1 you get like this. So on and so forth. So basically there are multiple cases where we would like to use these kind of thresholding algorithms. You know, binarizing images, like basically creating it into a binary. Binarizing is one of the principal steps of any sort of image processing algorithms. And there are certainly like more complicated versions of this thresholding. One is called as oath binarization. So I urge you guys to just go look into it later. I mean, I won't go into too much, but basically Oath-Seuss binarization deals with selecting a threshold like arbitrarily. So here we set a threshold of 127. That's a global threshold, right? So global in the sense it'll work on all images. But sometimes we actually wanted the threshold to be case specific. Like in some sort of image processing algorithm, we'd want like one specific threshold and another specific threshold based on the distribution of pixels in that image. So sometimes we'd actually, like, how do I say, actually very, like, implementation dependent. In some implementations you'd actually want the threshold to be set based on the distribution of the pixels. So might have in some image a lot more white than black. So in that case you might want to set your threshold much higher than the midpoint. In some cases you might have much more black and you want to set your threshold low. So Oath-Seuss will basically find the best threshold which you need to use for your image based on the frequency of pixels in your image. And then it'll set a midpoint and do it. RGB space to grayscale space. So one way of doing it is basically taking the mean of R, G and B. So you do R plus G plus B by 3, but this doesn't work. Any ideas why? Yeah, so we got the right answer there. So what happens is, when we deal with images, we have 3 channels. Thing. 1, 2, 3, 255, 2, 3, 255. So what we do is we do R plus G plus B by 3. 1 plus 1 plus 1 by 3 is 3 by 3, which is 1. 2 by 2 is 2. It works very nice. But when you do 255 plus 255 plus 255, right? So what happens is this actually goes more than 255. But anything more than 255 is still treated as white. And 255 by 3 becomes something like 80. So you'll get like some sort of garbage value basically, where it's supposed to be white, you'll actually get an intensity of 80 and all that. So it actually doesn't work. So like the workaround to this is you individually do so that's actually what we do. So that's actually called as the mean method. There's also another method called as the luminosity method, which we use to convert a RGB image to grayscale. So in luminosity, basically the fundamental idea is that your human eye is not really equally sensitive to red, green and blue. It's actually more sensitive to green than red than blue. So we use this thing to actually make the images look more appealing to humans, since at the end of the day all of this analysis is for humans, right? So again, splitting it into each channel. So how many of you guys are comfortable with Python? Just show of hands. Okay, so there's a fair bit of Python coding going on here, and it's pretty simple to understand. Okay, so I just basically use this example to teach you guys. So in Python, what we do is, say we have a 3D matrix. So the first two things you see colon, right? Colon basically means all. Colon means it basically take all the things, and colon 0 means takes the 0th thing. 1 means it takes the first index, 2 takes the second index. It's basically RGB, right? So BGR, sorry, my bad. BG and R. So basically you just slice it and you take out each individual channel and then you perform your analysis on it. Okay, so this is basically how we deal with images on Python. Okay, yeah, so this is our original image. This is our mean and luminosity. I don't know if you guys can see, there's actually a little bit of a difference here. Okay, if you look at it close up, you'll actually be able to see that this image is a lot more vibrant than this. So in case you guys try it out in your systems, you'll be able to appreciate. Get extraction of a particular color from an image. So for this, I'd heard an answer from someone saying there's something called as an SV space. So do you know what H, S and V stand for? Yeah, hue, saturation and value. So intuitively, what do you think the hue is? So we just don't look at the words. I've actually put the answer up, but just try to think and tell me, when I say hue, in English, you'd probably associate it with color. But can you actually try telling me what you think hue is? Okay, good. So hue basically tells us in what region that color lies. So how many of you are familiar with the color wheel when you were young? Yeah, so there was that red, green, blue, right? So this is basically our color wheel. Okay, basically goes from 0 to 360, and each slice will represent a particular color. Okay, so the red color is represented by this sector, blue is by this sector, green is by this sector. That is what the hue refers to. So saturation will just tell us how saturated that color is. Is it like an intense red or a dull red? Okay, or an intense blue, dull blue. And yeah, that is saturation, and intensity is how bright is it? Is it really bright or really, not so bright? So Saturation will just like, it's like adding water to your paint. Okay, so if you add a lot of water, you get a slightly lower color. If you add less, you get slightly darker color. And intensity is just like how much concentration of color you actually use to mix in. Okay, so this is actually a lot of advantage of using hue, saturation and value. So can anyone think why we would use hue, saturation, value ahead of RGB? Try thinking. So, okay, say we want to extract a color from an image. Okay, so what would be your preliminary analysis of doing that? If you were working in with some image, how would you extract a particular color from an image? Like I give you a picture of the room and I will tell you I want all the blue from this room. How would you do it? Okay, so you will take the blue channel. But okay, there's something wrong with that, because let's say you'll get only like, so once you take out the blue channel, you'll get 0 to 255 all blue values. But then 0 to 255 is just a grayscale image, right? You can't really represent how dark or so. What do you say, 0 is very less blue, 255 is very dark blue? Can you really say that? It's not really possible, right? You just get 0 black, 1 white. So we just extract a blue channel. So what we actually do is use HSV. So in HSV, that sector of blue, we'll just like, slice it like a cake and take it out. And then we'll have to deal with only one matrix instead of 3. In RGB, if you really think of it, you can't really use these separately because you lose on a lot of other information. So again, everything will be like confined to 0 to 255 and actually get grayscale. In HSV, if you take out this sector, you'll get all the blue portions of that image and be able to perform whatever operation we want on it later. So, the test image, all the so we set our HSV range as 0 to 10. You basically just made range here. So this is basically the range for HSV range for red. You can just Google it and you'll be able to get it. We do something called as a bitwise operation on image. So I'll just talk to you about what bitwise operations are now. So today we take our image and now we take some numbers. Okay, so we take the hue. This is basically the hue of all the images. Okay, and whatever is in our red range, we just set it as high. Okay, now we set it as high, we keep it. Do you remember the truncation thing we did earlier? So whatever is low, we set it as 0. It's basically outside our red range. Okay, so don't really 0 to 10, right? So basically set all these to 0. 0, 0, 0. These all become 0. And basically we'll get this. Okay. Now we take a copy of the image and we do an AND. Okay. So when you do an AND, you just say, okay, whenever it's greater than 0, you set it as 1. So when you AND this with this, what you end up with is only your red portion of the image, and that is what this output is. Ask, which is basically only those values which have your red component. You AND it with your image, you're able to get this. So similar to AND, you can do a bitwise OR, bitwise XOR, and so on and so forth with all sorts of images, and there'll be like individual like implementation of each. So this is like a random row of this image I selected, you can see like it contains so many guys. Okay, I took one there, which is actually 255. So the 300th row contains like so many 255s in the is what you see here. Yeah. Next, I'll be talking about blurring an image. So you can see this image, right? It's pretty blurred. So try looking at it like your eyes like half closed. Do you think the image looks a little better? Yeah. So okay. So can you tell me like why the image looks somewhat better? So what exactly happens when your eyes are half closed? Anyone? It deals with something I talked about at the beginning of my presentation and how you deal with images. So you guys are familiar with sampling, right? So what happens when you close your eyes somewhat? Yeah, you're reducing your sampling rate. So sometimes when you have like a lot of pixels, we don't really need so many pixels to tell us information. Half the number of pixels might also be able to convey some amount of meaningful information to us, so we actually just reduce the sampling rate. There's also something else called as blurring. So that's what I'm dealing with. Something called as okay, I'll go into a Gaussian blur. First talk about different types of blurring. So blurring. So the first one is mean blur. So blurring, basically what you do is like smoothing out an image, okay? I mean, you guys might have played around with it in some sort of image software. So try to think of an example. Okay, so you guys, you know what bokeh mode is, right? Basically bokeh mode takes like your portrait images, whatever's in the foreground you leave it, whatever's in the background you blur it. So how exactly does blurring work? So you take a pixel here. Okay, so this pixel is actually pretty like high. You calculate the mean of all the elements around it. Okay, you calculate the mean and you replace this middle value with that mean. So effectively, what happens is it like smooths out the image. It reduces the amount of gradients and those kind of things on your images. So if you had like a very sharp image like this, it'll somewhat become a little more smooth. So that's what a mean blur does. It just takes the mean of all the elements around it. The next thing is a Gaussian blur. So do you know what Gaussian kernel is? Yeah, it's like a bell curve. Okay. So what do you think the advantage of a Gaussian blur over a mean blur is? Focusing? Okay, so why do you think focusing is better? So what are you focusing on? Someone just say it out loud. You can feel free to guess. I don't, it's wrong also, no one's going to judge you or anything. So when you're focusing, okay, so do you know what a Gaussian function is? Okay, so here we calculated the mean, right? So what we do is we put a Gaussian matrix. Okay, so two-dimensional Gaussian matrix looks something like this. Okay, so okay, maybe now you guys might have a better. So this is like a 2D Gaussian matrix. So in 2 dimensions it would look like, okay, basically like that kind of mountain. So zero. Yeah. What do you think is happening here? Yeah, so that's precisely what happens. So whatever is nearer to this central pixel, we're giving more weight to it, okay? And whatever is further away, we're giving lesser weight to it. So actually we can do this in both ways. Here we're just taking a gradient like along this direction. You can actually take it along both directions, like decrease these values also. And so basically it removes radially outward. Outward in the sense I'm decreasing the intensity as we go further and further away. So you're actually focusing on pixels closer to your actual pixel you want. So this is what a Gaussian blur does. So local information is actually preserved when we do a Gaussian blur. So one sec, this is the original image, and you can see that it's been slightly blurred when we pass this Gaussian kernel. So how do we actually apply this Gaussian kernel to our whole image? So what we do is we create a Gaussian window, okay? So this is whatever I rep, so like a 5 cross 5 Gaussian window. And then we superimpose each part of our image, okay? Then we calculate an element-wise product, and whatever output is, we replace the set pixel with that value. This is actually how you use a Gaussian kernel. So later on in your course, you'll all learn about correlation and convolution and stuff. So I don't want to go too much in depth with those concepts, but that is actually how a Gaussian kernel is and like what it does and stuff. So in order to be able to understand what's going on, you want me to repeat how this Gaussian kernel is being used. Everyone's good, right? Okay, awesome. Use of this Gaussian kernel. So you can look at this image here, right? So it's pretty noisy. So what do you think is going to happen when we apply a Gaussian blur on this image? It actually looks a little better now. It was look pretty grainy. This graining has been much more reduced. So there's also something called as a median blur. So you have mean median mode, right? So here instead of replacing all the elements around with the mean value, we replace it with the median value. So this is especially useful in something called as salt and pepper noise in an image. So what is salt and pepper noise? It's actually like, if you think of it, it's just salt and pepper. You take a handful of salt and pepper, it's white and black, and your image has random like pops of white and black. And like when you take the median of the values around it, it'll actually help. So just give you an example of how it actually works. So we have, let's say, a very smooth image. So some pixel values. And we have, let's say, a piece of salt in the middle of this image. The piece of salt will be represented as, say, 210. So you'll have like a very like smooth image, and bang in the middle of it there'll be this white pixel. So this is basically because of some data transmission issues or some other corruption of it basically. So when you take the median of these elements in this matrix, you'll get 27, 13, 18, 23, 25. Median value will be probably 35, I guess. This is actually writing it, but let's say the median value is 35, and we replace this with 35. So your actual image will actually look much better. So that's what we actually do, and this is what it looks like. So the opposite of blurring an image is actually sharpening. Okay. So wait, 1 second. Yeah. So we actually sharpen an image. So in blurring, what we do is, I told you, right? If you have like a very noisy thing, you somewhat make it less this thing. So in mathematical sense, what do you think that is actually doing? Standard deviation, or actually we're actually looking at the derivative at each point, and we're decreasing that derivative. Okay, so let's see, you have some function like this. So the derivative is changing very rapidly. Maybe somewhat median, the derivative is not changing as rapidly. So that's what blurring an image is. On the contrary, sharpening an image basically increases derivatives. So from this, you want to get to this. So that's what we do for sharpening an image. And our sharpening kernel is like this: -1, -1, -1, -1, and then 9 in the middle. So basically blurring, you replaced everything around it with this middle value. Sharpening, you just do the exact opposite. You calculate the difference and accentuate whatever's in the middle. is basically what the sharpened image looks like. Okay. Yeah. Next. So what these all are just filters. Okay. So in all sorts of signal processing, we'll encounter filters in all sizes and shapes. So I'll just give you some filters now. Just play with some filters and basically we'll see if you guys have like grasped whatever I've done today. Oh. So when I pass this filter in an image, what is going to happen? Speak up. Okay, you're saying it's going to be the same image. How many agree with him? So does anyone disagree with him? Okay. So why do you think it's going to be the same image? That's the right answer. This is basically an impulse. Okay, it's basically a impulse, a single impulse. In one dimension, if you want to represent it, basically this. And when you pass your impulse over your given function, you'll actually get back the same result. So basically an identity kernel. So basically you know that any matrix A times I is equal to A. So in image processing, this is your identity matrix. Okay. Okay, the next one. What is this going to do? Shift it which way? Left or right? It's going to shift all your pixels left. Okay. So this is just another example. I have a third one. Just look at it. So what is this going to do? Is it reducing intensity? Basically, yeah, it's mean. So basically you're blurring your image. This is basically your mean blur which you're applying on your image. So when you slide this over it, it's going to take the local mean of all the pixels around it and just replace it with that value. So okay, so let's play some other filters. So now okay, so I'm just doing 75 into this and I'm applying this filter on my image. Okay, and I'm going to tell you one thing here. If the product is greater than 255, truncate it to 255. So what will this do? It's basically 75. Okay, basically a matrix of 75s which I'm applying on my image. Does. Okay, I'm actually forgot to mention one thing. I'm taking this and I'm adding it back to my original image. Okay, so you calculate the product and you add it back to your original image. What I'll do is basically this. becomes much brighter. And similarly, when you subtract the 75, it becomes much darker. Okay, so yeah, so this is what I wanted to deal with. Okay, so I have another concept. I don't really have code for it right now, but when if you think of how you would resize an image. Okay, so basically, resizing means I have a 100 cross 100 matrix and I want to make it a 200 cross 200. So with minimal loss in information, I want to convert this matrix of 100 to make it of 200. Does anyone have any idea how you would do it? It's no right answer, there are multiple answers. If anyone can think of something, you just shout out. Becomes 4 cents. Okay, so what? Okay, so you could do that, but what will happen is it will become very patchy, right? You think of some other way, because now you're losing only local information. So if you have a 1 hit, you have like a, this will become 1 1 1 1. Okay. So it's going to be 1 and suddenly become 31. So it will become like somewhat patchy, don't you think? Think of any other way of doing this? 16. What? You understand? I didn't quite get what you said. Okay, 4 pixel repeat 4 times is okay. So it's actually wrong. Can anyone think why that's wrong? Yeah, so actually, like, you have a picture of a chair and you have this board. You have chair, board, right? So it's actually not going to work. So any other thing? Okay, so you take 1 and 50 and you put a 51, and then you put a some other whatever, you put that value there. So now this is going to be 100 cross 100, and if you take 2 at a time, you will get 99 pairs, right? So now you got 199 cross. I wanted this. So it's not really, it's okay, it's doing the job, but do you think of any other? Okay, how do you turn this 199 into 200 cross 200? Yeah, so one possible algorithm would be to just repeat this row here, repeat this row here. I mean, this is basically like a brainstorming session. I'm not saying there's one right answer, one wrong answer. Just seeing what you guys can come up with, just to see if you'll be able to grasp whatever I've done today and stuff. So, you all know what interpolation is? Interpolation? Okay. Yeah, so basically if you have like one value, you have a function. Okay, my bad. You have a set of points. And you want to like fit a graph through it. And you don't know this, you just know at 1, at 2, at 3, at 5. You don't know what the value is at 4. So actually what you do is something called as interpolation. So linear interpolation, you just draw a line and see which is the best fitting line. In quadratic interpolation, you draw a quadratic function, and as you go to higher and higher functions, you'll finally get a nice curve that goes through all your points. Similarly, you can actually use interpolation, because let's say it was 199 plus 199, and I wanted your target image to be 100 cross 100 to 157 cross 157. So, I mean, now what will happen is, you will take pairs. You get 199. No, you either have to reduce 199 to 157, or you have to take only specific pairs. Okay. So again, that's going to lead to issues, right? So So what we can actually do is we can interpolate values using a small window of our size. So all of you are familiar with like your vernier calipers and stuff, right? So you basically have a window of like 1 to 10. You have another window like smaller one, and you keep sliding it from 1 to 5, and you can actually get any number of values you want. So we can actually use that similar concept here, and we'll actually be able to get 100 cross 100 to 157 cross 157 and interpolate in between values if and when needed. So if you have like a 1 and a 10, you can maybe interpolate values in between to get maybe like a 7 or a 6 and 9, 3. Because basically based on how that image gradients are changing, you can actually get this. Okay. So just mind if I continue a little longer, then I'll just stop. So next thing what we'll be looking at is edge detection. Okay, so do you guys know like how you can detect edges in an image? Yeah, so basically that's the answer you're looking for. So it's actually a gradient change by a large value. Okay, so let's say you have an image of something, let's say that board. Okay, this blue, and then there's two brown lines, right? So you'll find the gradient of pixel intensity. So can you actually come and tell me like how you will do that gradient on this image? You can write it down or something. You can actually think how would you actually find the gradient in an image? Like normally you'll just do d by dx or d by dy, but what we have here is a digital representation, so you can't actually find a gradient or a derivative. How exactly? Okay, so you can subtract, or instead you can also use a window. Can you think of some window which when you pass over your image will calculate a gradient? Okay, like this. Okay, so, yeah. So you pass it. And then what will you do? So once you have your gradients, so you just basically have minus 10s, and then what will you do next? I've actually studied it before or something. Oh, okay. So, actually, that is the answer. So, user. Or you can actually make this a 2 if you want to like increase the gradient in values. So when you pass this over your image, you'll actually get gradients. I mean, please, like if you've already studied this, just don't like interrupt. So, what do you think this will detect? What kind of edges will this kernel detect? Detect vertical edges. Okay, so So if you actually look at this image, it's going to be like something dark and something bright, okay, like a line in between. Okay. So basically you want to detect this edge. Okay, so you have to pass some kernel. So wait, first what they said was element-wise difference. So basically if you take an element-wise difference, take it and subtract it with the pixel on the left. Okay, but this has nothing on the left, so just do it on the right, because 10 minus 10. 90 minus 10 will give you 80. 90 minus 90. So basically this is how we detect an edge, do by element-wise subtraction. So that's basically finding a gradient. Okay. So actually what we can do is so the thing is we can't really, it's computationally expensive to sit and calculate an element-wise subtraction each time. If we actually use matrix multiplication, it will become much simpler and much faster. So when you do this 1 minus 1 0 1, what will happen is 10 minus 10 0, 20 minus 20 0, 10 minus 10 0. Okay, so basically 0. Again you do, okay, then what I imagine there was another row of tens, so you get probably 0, bunch of zeros here. But here like what will happen is you get 90 into 1 minus 10, so you'll get actually 100. Okay, similarly, sorry, 90 minus 10, 80. Similarly again 90 minus 10. And if you have another bunch of 90s here, it will again go back to 0, 0, 0, 0. So actually when you pass this over your original image, you're getting these bunch of 80s, which basically means that is where your edge is. Okay, so we'll actually be stopping the cases here. There are some more concepts in image processing, so if you guys are like interested, I could possibly like take it up on another day, but I could also like set up an actually, so wait, you guys are free, right? So if any of you like are interested in the Python aspect of it, maybe like I could actually go through with it, you guys go through it. So I got interested in doing that. There's actually a bit of coding involved. So actually the thing is, coding is basically a tool we use for image processing. So we actually already studied image processing, you don't need to stay for that part. I'll just talk the code through with you guys, with those who aren't really able to understand. Okay, so can you have the code again? Just push. Okay, so peace. So I'll just be starting with, so okay, now what I'll be doing is actually like some OpenCV tutorial. So we actually studied OpenCV before. I mean, you can actually like, quick lines, you can just stay, yes, as everyone just stay. So I'll actually have to just Google the code myself. Yeah, okay, that is. 1 sec, I should have it. Basically there was a chessboard image, right? So when you actually apply an edge detection, you'll actually get these edges in Y, these edges in X, these edges in both. So wait, just 1 sec. Let me just do. Yeah, so actually this might be easier for you guys to understand. So when you actually pass your kernel over your image, this is how your edges in Y and edges in X would look when you do the detection. Yeah. Okay, so go back. Okay, so first, okay, so can you all see this cell? Is it visible to all of you? Zoom in a little bit. Okay, so first, whenever you're starting with Python, we need to import libraries. Okay, so NumPy and Matplotlib are two libraries which we'll be using throughout. So NumPy basically helps us to deal with matrices, and Matplotlib helps us to plot. So I wanted to create this chessboard image. So what you do is np.zeros will just create the 16 by 16 matrix of zeros, and then you just run a for loop, and then you just add the I and j value in modulo 2, which will give you zeros and ones. Okay, so yeah, I actually talked about it earlier, right? So wait, just give me a second. And yeah, here this is just PLT.im show just shows you your image. Color map gray just sets it to black and white. Otherwise, you leave it, it'll like use Matplotlib's default, which will make it blue and red. So that's what we do. So one sec. This is basically your randomized image. Okay, so basically what it did was bool.getRandomBits. Instead of doing I plus j modulo 2, bool will get a random 0 or a random 1, and if I run it again, you get like a different thing. So can you like actually think of a real world application of this thing? Yeah, it's basically your QR code. So not exactly a QR code, but basically you can just put out random things. Actually information is encoded, but similar to that way it works. Okay, so basically this part we can skip. So let's now look at reading images. So basically we use OpenCV for this. So this is import cv2 is a library, so you'll have to make sure that you have all this installed. Okay, so you'll have to install Anaconda and all that. So I can actually put up some links for you in case you're interested, in case you want to install Anaconda and install OpenCV. Just do cv2.im read, comma 0 will just read it as a grayscale image. Change it to 1. Will become color. Oops, my bad. Same issue. So basically 1 will read a color image. If you put a 0 there, it's a grayscale image. So that's how you read an image. Okay, so you have to make sure that this path, whatever is there, images lena.jpg, you have to actually have a folder like, yeah. So I have this folder images with so many images there. So you all actually have to make sure that it's there in your system with the same hierarchy, otherwise it won't work. Yeah, and again this is just printing dimensions. So okay, so this is basically how you extract channels from an image. So in Python you have 3D matrices, and if you say colon, it will just select all elements. 0, 1 and 2 will just like, you imagine you have like 3 things. 0 is the first set of 220 values, 1 and then 2. So basically how you select matrices. In C you will say 0, 0, 1, 0, 0, 2, right? Same way. Python is just everything is vectorized and makes it much simpler. Yeah. So some code here, you guys can just actually try plotting, see what happens. Yeah, so this is basically to swap this colon -1. Basically -1 is basically refers to the last column. So 0 and -1, yeah, the last axis. We'll just swap those two. So then you get this. So basically like how you swap an image without that convert color function. And yeah, that is good. Again, same way, import numpy, import OpenCV, read your image. And here you create your, this is basically your thresholding, right? So basically when you threshold, you'll have to pass your image. 127 and 255 is basically the max value, 127 is your threshold, and this is basically the kind of thresholding you want to do. So there's thresh trunk and there's like a couple of more. Thresh to 0. What do you think is going to happen when I do thresh to 0? Anyone expects? What do you think is going to happen? Okay. Any other guesses? Basically, whatever below threshold to 0, above we just retained it. So this is basically what we used in our color extraction, right? So whatever was there in our red range, we retained it. Whatever wasn't there, we changed it to black. So thresh to 0 inverse, we'll just do the opposite. Then R plus G plus B. Basically you take 0, 1 and 2, red, blue, green channel. You calculate the mean and you have to, this as type uint8 is basically like you assign it to an 8-bit integer, 0 to 255. We don't want floating points, right? Because when you do 0.33 into 1, you'll get 0.33 plus 0.3 is 0.99. And when you try representing floating points, you'll get garbage values. So actually, this is actually like as type uint8 will convert that 0.99 into 1 or 0. Basically, you typecasting. Basically, this is typecasting in Python. So, the original image, mean and loop. So, okay, now that I've zoomed in quite a bit, you guys can actually be able to see a difference, right? Slight difference. This is slightly more dark. This is a little brighter. Yeah. Okay. Yeah. Extraction of a color. So we create a array of our hue, saturation and value range. We create a mask. cv2.inRange will just use this. HSV is basically our image, and whatever is in this range, it will create the mask. Now it is bitwise and. Yes, basically just a lot of reading. There's no coding involved. It's just understanding how this code actually works. Yeah, there we have it. Yeah, blurring an image, again, same way. So just there's a function called cv2.Gaussian Blur. So 5 cross 5 refers to the size of our window. So I'm going to do 11 cross 11. Can you expect what is going to happen now? Okay, you're saying this is going to be more detailed. Any other guesses? Going to be more blurred, okay? Cool. So, truths. It's actually more blurred in this case because you take 11 cross 11, you're taking a wider range, so it gets a lot more flattened out. Okay. And again, if you do 3 3, it's a little less blurred. Basically, this application of this Gaussian kernel, and yeah, so that's actually it. Sharpening an image. Okay, there's actually just one more concept, so I guess I can actually finish it now itself here now. So what it's actually called is template matching. Okay, so let me just run this. Okay. So basically we have this image of your eyes. Okay, so basically these are the images of that lady's eyes. This is your image and you want to find out where in this image these eyes occur. Okay, so there's actually this technique we use called as template matching. So that is what is done here, and when I run this snippet of code, see, it drew a box around her eyes, right? So can you actually, okay, so how does template match actually work? So for this we'll actually use the concept of correlation. Correlation is something you guys will study later on if you're in EC or EEE, but it's like a simple way of how it actually works. So say, just for the sake of convenience, Lena's eyes are represented by this pattern 10, 90, 10. Okay? So when we extract, we take that, when we crop out that 10, 90, 10, we take this and we start passing it over the image each pixel. Okay? So let's say we have at some point 70, 100, 10, something so on and so forth. You just take this and you start calculating the product, and whenever the product is actually the highest, is actually your highest correlation. Basically correlation means how much similarity is there between two images. So if you have a one signal, sinusoid, writing it over this one, and when there is maximum matching between these two, they'll actually, right? So basically, let's say you take the product each you here and you just plot it. So what you'll actually get is the same sinusoid with an increased amplitude, right? But what happens when you do with, what are you going to get? You get 0, right? Basically this and this will interfere destructively, and you have this, and this is slightly shifted. What is going to happen? Yeah, you basically get a slightly different sinusoid. Basically, if you have sin x into sin of x plus theta, you just do sin A, sin B is sin A cos B, or sin A cos A cos B minus cos A cos C. So it will just be another type of sinusoid with another type of distortion. So basically, if let's say now once you have these outputs, you just calculate the area. Again, what if you flip it and get a positive? So whenever this match, you get the highest area. Whenever this are destructive, you get the lowest area, and in between you'll get some in between values. So your correlation will actually be like this, and this represents maximum matching. So we do the same thing with our image. Okay, so you have that I matrix and you start passing it over your image. Whenever it matches with the actual image, it will give a high output, and when we get that high output, we just plot it, and that's what template matching actually does. Okay, so that's it. I'll be ending the cases here with that. If you guys have any doubts, you can always come and reach out to me or drop me mail, WhatsApp, whatever. Okay, that's it. Yeah, good.